Okay, I'll wait for 5 more minutes and then probably start the session. Okay, so I waited for 5 minutes and I guess I'll start the session now. So welcome to the live session, week 3, Signal and Systems, NOC24 EE-28. The instructors of the course are Professor Hitesh Shremali and Professor Kushal Kesha. And yeah, uh, I'm Yawar, a PhD student at IIT Kanpur. Yeah, these are the guidelines as usual and the prerequisites. The prerequisites include the last week's lectures that covered the following topics: the frequency domain representation, the Fourier transform and the inverse Fourier transform, and the frequency time uncertainty relation. Okay, so I hope that you have already attempted the assignment 3 before watching this session in the recorded form. So the Fourier transform is an integral transform that converts this function x of t into a form that describes the frequencies that are present in the original function. Okay, so the output of this transform is a complex valued function of the frequency. This term Fourier transform refers to both this complex valued function and the mathematical operation. So in fact, this Fourier transform is sometimes called the frequency domain representation of the original function. So if in the question, uh, at times you will be asked to find the frequency domain representation of the original function, that essentially means to compute the Fourier transform of the given function. Okay, and the functions that are localized in time domain, they have this Fourier transforms that are spread out across the frequency domain and vice versa. So if a function is localized in the time domain, it would be spread out in the frequency domain. Likewise, if the function is localized in the frequency domain, it would be spread out in the time domain. So this is the frequency time uncertainty relation, which I'm sure you all would have gone through. So basic definitions, the Fourier transform is computed using this integral, and we denote it by f of xt such that this f of xt is equal to x of omega. And the inverse Fourier transform x of t is given by this integral, and we represent that using this f inverse of x of omega such that this f inverse of x of omega is equal to x of t. Okay. Also, there are some conditions for the existence of Fourier transform, right? In the last week's lectures, you would have seen these Dirichlet's conditions. Let me briefly go over them. So the signal x of t for which we are trying to find this Fourier transform should have this finite number of maxima and minima over any finite interval. And this signal x of t should have this finite number of discontinuities over this finite interval. And it should be absolutely integrable over any finite interval. That is, this integral should be less than infinity. Okay, so with that, we'll go through some of the properties of the Fourier transform. Uh, I guess you would have gone through some of these. For example, linearity. This is pretty straightforward. The Fourier transform is linear, and one can readily see that because the integral operator is linear, right? So it's reasonable to expect that this Fourier transform would be a linear operation. Okay. And the second one is this time shift. The if we have this Fourier transform pairs x of t and x of omega, then the following holds good. If we make a time shift in x of t by t naught, then that x of t minus t naught would have this Fourier transform. Again, the proof is simple, and I hope you guys would try the proof yourselves. I'll move on to the next property, which is duality. Given the Fourier transform pairs x of t and x of omega, we have following, right? So let me use, okay. So we have the following Fourier transform pair, right? The x of omega is the frequency representation of this x of t. Then it turns out if we will use the function in this frequency domain representation x of omega, x of t, that function the frequency domain representation of that function would be this. Okay, so I would again suggest you to try this out. It is again straightforward, and if there is any doubt, you can let me know via mail, or you can drop a comment in the recorded session and I'll address that. Okay, so the next one is this frequency shift. Just a minute. All right. So the frequency shift again, given the Fourier transform pairs x of t and x of omega, we have following property. Okay, so if you shift the frequency, okay, in the frequency domain representation of the function, in the time domain, it gets multiplied by e to the power j omega naught t. Okay, where this omega naught is the frequency by which the shift has occurred in the this x of omega. Okay, so again, you will try this out and let me know if you are able to get it. And probably in the course, you guys must have been taught this and most of these properties. Okay, so we'll not waste time in proving them again. But if you guys have any doubt, you can let me know and I'll address that. So the next one is the time scaling. The time scaling, if again, if x of t and x of omega are the free Fourier transform pairs, then this x of at, which is time scaled by this factor a, right? We are time scaling x of t by factor a. What would be the Fourier transform of that? It would be given by this expression. Okay, it's 1 over mod a x of omega by a. All right. And with that, we can start with the first problem. That is to compute the Fourier transform of e to the power minus 4 modulus of t minus 1. Okay, so given function is x of t is e to the power minus 4 modulus of t minus 1. And we need to find what is this Fourier transform of x of t, right? So we'll start by definition. We'll write that this, suppose this is equal to x of omega, then that x of omega would be equal to minus infinity to infinity x of t e to the power minus j omega t dt. Right, I've done nothing but used the definition. Now, uh, what we'll do first is we'll first compute the Fourier transform of e to the power minus 4 modulus of t, right? And then we'll use the time shifting property, right? Because one can readily see that these two functions are nothing but time shifted versions of each other, right? Here the time has been shifted by 1 unit. And once I'll compute the Fourier transform of this function, I'll then use this property. Let this be denoted by x1 of omega. Okay. So what is x1 of omega? It is minus infinity to infinity e to the power minus 4 modulus of t, right? I'm using this x of t here. E to the power minus j omega t dt, right? And we know that this modulus of t function, this one, it is equal to minus t when t is less than 0, and it is equal to plus t for t greater than 0. So what we'll do is that we'll split this integral into two parts. Okay. Minus infinity to 0. Okay. From minus infinity to 0, t is less than 0, right? And for t less than 0, this modulus of t is for t less than 0, this modulus of t is equal to minus t. Okay. So I'll use that. At minus minus would make it plus, and we will be left with this e to the power 4t e to the power minus j omega t dt plus now the other interval, right? Minus infinity to 0 and now 0 to infinity. E to the power. Now, modulus of t is equal to t for t greater than 0. Okay, so I can now replace in this interval the modulus of t by t. So I'll be left with this e to the power minus 40 and e to the power minus j omega t dt. Okay. And now what is minus infinity to 0 e to the power 4t e to the power minus j omega t? We can simplify this minus infinity to 0 e to the power. What I'll do is I can write it 4 minus j omega t dt, right? And similarly, it would be 0 to infinity e to the power minus would be common. It would be 4 plus j omega t dt, right? Now, this would mean that e to the power, this integral evaluates to following e to the power 4 minus j omega t whole divided by 4 minus j omega, and the limits are from minus infinity to 0. Okay, and then we have this e to the power minus 4 plus, this integral is given by this, and now I'm writing the result of this integral. E to the power minus 4 plus j omega t whole divided by 4 plus j omega and a negative sign, right? Because the coefficient of t is this minus times 4 plus j omega. And what would be the limits? The limits would be from 0 to infinity. Okay. So again, we are trying to compute this, right? X1 of omega. And our ultimate aim is to get an answer for x of omega. Now, what is my x1 of omega? X1 of omega is, now we'll put in the limits. When t is 0, see 1 by 4 minus j omega can be taken out. And we are left with 1 when t is 0. And when t is minus infinity, this would be 0, right? Now, similarly, now in this case, when t is infinity, t tends to infinity, we'll agree that this function should tend to 0, right? Again, what I'll do is, see what I'll do is, I'll I'll interchange the limits. There would be a negative sign and I would multiply that negative sign by this negative, right? So let me show that step as well. E to the power minus 4 plus j omega t whole divided by 4 plus j omega. And what is this limits? Limits would be from infinity to 0, right? We interchange the limits and took out that negative sign. Now what is this? X1 of omega would be 1 by 4 minus j omega. What about this? Would this be 1 by 4 plus j omega? See, when this t is 0, this would be 1. And when this t is infinity, this whole thing would tend to 0, right? So it would be 1 minus 0. 1 minus 0 is 1. So we get this answer, right? 1 by 4 minus j omega plus 1 by 4 plus j omega. In fact, we can simplify this one. So x1 of omega, which is essentially the Fourier transform of, let me copy this, okay, so that we don't lose the track. Okay, and what is the answer? This can be simplified to following. You'll simplify this, you'll get 4 minus j omega, 4 plus j omega, and then we have this 4 plus j omega plus 4 minus j omega, right? This j omega and j omega would cancel, right? Plus j omega would cancel with this negative j omega. You are left with 4 plus 4, and that evaluates to 8, right? And in fact, this is 8 divided by omega square plus 60, right? I use this a minus b times a plus b. This is a square minus b square, right? Here a is 4 and b is j omega. Rest you can figure out, right? So on simplifying this, you would get this omega square plus 60. So what is our x1 of omega? But what was our original goal? Our original goal was to find this, right? So let me write this x of omega. What is this x of omega equal to? Okay, if this is x of t, okay, wait, let me first write this. I mean, this x of omega by definition, the way I have defined this is modulus of t minus 1. Am I right? Or yeah, this is what x of omega is by definition, and this is what we wanted to compute. So if this is x of t, do you agree that this would be x of t minus 1, right? And you can refer to the slides, and if you guys remember, I showed you this property, right? Given x of t and x of omega Fourier transform pairs, we have this x of t minus, in general it's t naught, but I'll use t minus 1, right, for my case, because t naught is 1 for my case. What is that? That is e to the power minus j omega t naught, this x of omega, right? So yeah, so what we'll do is we'll multiply this factor. In fact, this t naught is 1, right? So I should write, and okay, yeah, would be this e to the power minus j omega times this x of omega. So what is x of omega? X of omega would be e to the power minus j omega times the Fourier transform of the signal that is not time shifted. In our case, the signal that is not shifted is this x1 omega, right? So we'll write this 8 whole divided by omega square plus 16. Right, this is the answer. Pick. Okay, so which option is correct? The correct answer is this one, right? 8 by omega square plus 16 times this factor e to the power minus j omega. Okay, so I'll move on to, okay, let me briefly show you an important result that you will frequently be using in this course. Okay. Uh, That is this result. Okay. Given the rectangular signal, this rect of t by tau, which by definition is equal to 1 in this interval, minus tau by 2 to tau by 2. Notice how I have used the notations, right? Uh, in one of the sample problems today, I'll be making use of this function. So make sure you have this in mind, right? I'm defining this rect of t by tau. This tau is nothing but the interval over which this function is 1, right? It's 1 from minus tau by 2 to tau by 2, right? So the interval is tau by 2 minus tau by 2. That is tau, right? So the result is that the Fourier transform of this function is equal to this tau sinc of omega tau by 2. Okay. And you can go through some definitions, right? Like what is the main lobe and what are these 0 point crossings? Uh, and what I want you guys to do is to use this duality property. Okay, you'll use this duality property given that this small x of t is this rect of t by tau, and this x of omega is this tau sinc of omega tau by 2. Okay, this would be, I would say, a homework. You can let me know the answer in the comments. What would be the exact expression of this one, right? In other words, I want you to find this f of t, f of m, right? Using the duality. Okay, we'll now move on to the next question. So the next question is the sinc of theta is 1 at which of the following values of theta? Uh, I guess this is pretty straightforward and I expect you all to know this. Can anyone let me know in the chat what should be the answer? Where is this sinc function equal to 1? Right, at theta equal to 0, right? So let us spend some time on this sinc function, since this is an important function that we'll be learning in this course and using it time and again in this course. So sinc function, we have the unnormalized form and the normalized form, right? This is unnormalized form and the normalized form. In unnormalized form, we define this sinc of theta to be equal to sine of theta by theta when this theta is not equal to 0, right? And we define this sinc of theta to be equal to 1 when this theta is 0, right? Can you guys see that this 1 is actually the limiting value of this sine of theta by theta? When theta tends to 0, what does this sine of theta by theta tends to? I can use L'Hopital's rule, right? And see, I'm telling you what is the limit theta tends to 0. Sine of theta by theta. That is limit theta tends to 0. By L'Hopital's rule, I would differentiate the numerator and denominator. It would be cos of theta by 1. And what about this? Now I can readily use this theta equal to 0. Why? Because the function would not be of indeterminate form. cos of 0 is 1. Whereas if I would have used theta equal to 0 here, this would have taken 0 by 0 form, right? Which is indeterminate. So the way we define the sinc function is that we assign the limiting value of theta equal to 0. Sinc, if we define sinc by this function, then it is not 1 at theta equal to 0. In fact, the limiting value is 1 at theta equal to 0, but we then I would say define it to be 1 at theta equal to 0. I hope I was clear. Okay, so the correct answer for this one was this theta equal to 0, which you guys pointed out in the chat. Okay, now the next question. What is the unit step function? Sorry, unit step function in time domain. What would be its frequency domain representation? Okay, before this, I will show you something else first. Does anyone know what is the Fourier transform option for? Yes, that is the correct option. So, how did you came to the answer? Could you just briefly mention that by unmuting yourself or just writing in the chat itself? That is the correct answer. Option 4 is right. But okay, fine. I'll go through the method. Okay. So before this, what is the Fourier transform of delta function? Where you guys taught this? Right. Essentially, what I'm saying is
It's one.
it's 1. Yeah. The Fourier transform of delta function is 1. I guess you guys know that, so I will not waste my time in proving that. So x of omega is 1. So delta t, this is the Fourier transform here, right? Delta of t in time domain is 1, a constant function in the frequency domain. Yes, the other guy as well said 1. So by making use of the duality property, can you guys tell me what should be the Fourier transform of 1? Notice you cannot readily use
Pi into del of omega.
I into del of omega.
Actually, it's minus omega, but it's even. That's why minus omega equal to
Yeah,
plus omega.
delta function is even function, so we can write delta of omega. In fact, the correct answer is 2 pi del of omega. Why? Because remember this, the factor is 2 pi, right? That is why the Fourier transform of 1 would be 2 pi del of omega. Okay. So let me start with the proof. We need to discuss this one. Okay. Have you guys computed the Fourier transform of signum function? I mean, given x of t, what is x of omega? Yes, it is 2 by j omega. So I would readily use that result as well. Okay. And then make use of properties to find the Fourier transform of unit step function. Okay, so we have following thing, that this signum function, the Fourier transform of that is 2 by j omega. Okay, and we also know that this unit step function u of t, we can write that as half. Agree? Because this is unit step, this is signum. What would happen if we take this? If I use this half of signum, this would be half, half, right? Amplitude scaling. And then if I DC shift this signal by half, this would be 1 and this minus half would be 0, right? Essentially, if we add plus 1 by 2 to this signal, we get this unit step function. So we can write this. Now, what we'll do is, we know that in general, if we have a constant a, what is the Fourier transform of that constant? That is a times 2 pi del of omega, right? If you don't get this point, you can multiply both the sides by a, right? You'll get this. Okay, so if we know this, we can write Fourier transform of u of t. What should this be? This should be Fourier transform of half plus Fourier transform of, right? This this one is, I'll use this result, half times 2 pi del of omega, which is nothing but pi times del of omega. And Fourier transform of this half of signum of t would be, I'll take this half outside. What is this Fourier transform of signum function? That is 2 by j omega, right? So this is 2 by j omega. And this 2 and 2 would go. What we'll be left with is Fourier. You would be left with 1 by j omega, right? And that was the required answer, which was answered in the chat as well. The Fourier transform of unit step function is 1 by j omega plus pi times del of omega. Okay, let me show you alternative way of doing this. Would anyone tell me why I did not use this original definition, right? Because in a question before, I used this definition, right? Can I use this to evaluate the Fourier transform of u of t? In other words, can I replace this x of t by u of t? My claim is that I cannot do so. Which condition is violated?
Integration should be a finite one.
Yeah,
X of t.
it won't be absolutely integrable, right? This condition is violated, right? The function is See, the function is 1 throughout, right? And when you'll sum it, it would be infinity, right? And not less than infinity. We need this integral to be less than infinity. Okay, so that is the reason we were not able to use the original definition in computing the Fourier transform of u of t. But we can do some manipulation. Manipulation like this is u of t, right? What if I multiply u of t by e to the power minus ct? What is e to the power minus at, right? E to the power minus at, I mean, it is this, but would be zero, right? This product would be zero here. So I'm showing only in this part. What about this one? He made a comment that the function was not, this integral was not absolutely integrable. What now? Would u of t times e to the power minus ct be absolutely integrable? Do you see that this area is converging? Right, it converges,
Yes.
right? Theoretically,
Uh,
theoretically, when t tends to infinity, this would tend to zero, right? And this product would also tend to zero when t tends to infinity. So this function is absolutely integrable. Now, what limit should I take on a such that this would be u of t? What should be limit on a? A should tend to,
0.
yeah, a should tend to zero. Let us write that. So u of t is limit a tends to zero, x of t, right? And x of t is this. And when a tends to zero, we get u of t back. So what we'll do is we'll proceed with this function instead of u of t. And, and then we'll obtain the Fourier transform corresponding to this function. And then we would take the limit a tends to zero in that Fourier transform and then see if we get back this answer. Okay. Would you guys want to try this out? I'll wait for a minute. Okay. I'll wait for a minute and then start doing it myself. You guys should remember, in fact, this result, right? It is one of the basic results. What is this result? Fourier transform e to the power minus at u of t. What is that? Should I show this? How it comes? I'm sure you would have done this in week lectures, right? Have you guys seen this? Okay. So what we'll do is we will write this. Let's multiply. Let's convert it into standard form. Okay. So what I would do is I would multiply and divide by the complex conjugate. A minus j omega by a minus j omega. What is that? Agreed? Will I get this? So the conclusion so far is e to the power minus 80 u of t is a divided by a square plus omega square, right? Plus j times minus omega by a square plus omega square, right? I've just rewritten this. Okay. And then what I can do is if I take the limit, so let me think. What about this term? If we take the limit a tends to 0, what do we get? If I take the limit, what should this be?
J by omega.
J by omega, right? In fact, minus j by omega, right? Minus j omega. You missed out this minus sign. This would be, let's take another page, otherwise it would be confusing. So what I'm saying is, suppose I write this a plus b, where this capital A is this term and this capital B is this term. You all agree that this limit, this small a, this tends to 0. The capital B expression would tend to precisely this. How? I can readily use equal to 0, right? This won't be an indeterminate form. So I can write j minus omega. 0 square is 0. This would be minus j by omega. And we know that 1 over j is minus j, right? This is a basic result that I expect you guys to know, right? Have I made some mistake or none? 1 by j can be written as 1 by j times j by j, and ultimately we get minus j, right? Let's remove this part. We know this 1 by j is minus j. So minus j is 1 by j. So this limit a tends to 0. The b, this should be 1 by j omega. looks like we have obtained the part of this answer, right? What about this part? We are interested now in finding, use this one, limit a tends to 0, capital A. What is the limit a tends to 0 of this expression? Anyone would like to comment what should be at least the behavior of this? Graphically, the way I can approach this problem is to take the values of a, right? Let's say we are computing limit 0 plus. Okay, so I would take the value of a as 1 and then start approaching 0 and see how the behavior of the function is. Okay, I've done that and let me show you that part. So what do you guys think? Firstly, have I taken the form correct? It's 1 by, what was the form? This one, right? I'll take some values of a. Remember this from a by omega square plus j square, a square, sorry. So the form was a by a square plus omega square. And I mean, I've used x in place of omega for plotting purposes. But note when this omega becomes smaller and smaller, you can see that this approaches a function that kind of remember, right? What is this function? At least the black curve. What does this approach to? Suppose now I even reduce the value of it. Can you guys see what should be the limiting value of this? Would it be delta function? Do this exercise, okay? We'll come to the same point, but we'll do this mathematically as well. But the idea is you guys should at least know that it would be, this limit would be a times. I mean, I'm not sure about this constant of proportionality, but this would be this del of omega. Okay, so now what I would do is I'll write this limit a tends to 0. This capital A is this one, a by a square plus omega square, a del of omega. I hope the motivation for this part is clear. Okay, let's do one thing. We'll take the integral from minus infinity to infinity. Okay, we'll do that. I would get minus infinity to infinity a times del of omega. That would be equal to, right? And in fact, we missed out one this, right? I used, this is precisely what I did. It integrated both sides of minus infinity to infinity. And this would be k. What is minus infinity to infinity delta of omega d omega? What is this? In area, yeah. And what is area under the curve for this delta function? Right, we define delta function in that manner. Can in fact refer to tutorial session 1 I had shown in that session. By definition, we take this as unity, right? It's immaterial how this delta function looks. Yes, the area should be 1. Okay. And what about the right hand side? We have this a by a square plus omega square. Okay. And you guys realize that it is nothing but this tan inverse of omega by a. Okay. What you guys can do is do following. Put omega, I mean, put omega equals to z times a. I mean, this is nothing but scaling, right? I hope you guys can prove this part. This part is clear. Minus infinity to infinity, 1 by 1 plus x square. What is that? That is tan inverse of x. Similarly, you can arrive at this result using some substitution. Let's keep that homework as well. Okay. If not, you can let me know via mail and I'll address that. Now, this is k in the limits minus infinity to infinity. Nice. We forgot the limits. This is limit a tends to 0. This is again limit a tends to 0. Tan inverse of omega by a when omega tends to infinity. When omega tends to infinity, what is this? Tan inverse omega by a should be pi, right? Therefore, what I proved is limit a tends to 0, capital A, this expression. The limit small a tends to 0 gives us pi times, right? We had assumed it for intuition that it should be of this form, k times del of omega. Now this k is pi, so this would be pi times del of omega. Therefore, Fourier transform of u of t is pi del of omega, this capital A plus this capital B, right? Capital B in the limit a tends to 0 is 1 by j omega. So we again arrive at the same answer. Okay, so we saw two approaches, right? I'll write this as second approach. Okay, another question. Sine of 2 omega naught t plus j times cos of 3 omega naught t. I'll wait a couple of minutes and then start proving. Try to attempt this one. A hint is that this sine of 2 omega naught t, right? This argument. What is this by definition in terms of complex exponentials? E to the power j 2 omega naught t minus e to the power minus j 2 omega naught t whole divided by 2j, right? And likewise, the cos of 3 omega naught t, we can write that as e to the power j 3 omega naught t plus e to the power minus j 3 omega naught t whole divided by 2. Okay, I'll start proving it myself. So we know that this Fourier transform of 1, the Fourier transform of 1 is this 2 pi del of omega, right? We saw today this, and I'll use this. What if I use frequency shifting property? If I shift this omega by 2 omega naught, in time domain, notice we get this multiplication factor, right? E to the power j omega naught t. So I'll be using that. So 2 pi del of omega minus 2 omega naught, right? I'm taking care of this sign first. I'll break this into two Fourier transform of two quantities using linearity property of Fourier transform. So in time domain, we'll multiply e to the power j omega naught t, right? In our case, this omega naught is 2 omega naught. So we'll write 2 omega naught t. Okay. So likewise, I mean, we handled this one, the Fourier transform of this. Similarly, you guys can see this would come if we shift this frequency by plus, right? E to the power j minus 2 pi del of omega plus 2 omega naught. Okay, so you can use frequency shifting to get this and frequency shifting to get this. Now, for this sine of 2 omega naught t, I'll have this factor 1 by 2j. Which 1 by 2j factor? This one, right? This one would be out. What will be I left with? Fourier transform of this plus Fourier transform of this, but with a negative sign. What is Fourier transform of this? We saw that Fourier transform of this is this function. So I can write, in fact, I can take this 2 pi common as well because 2 pi occurs in both this and this. I write del of omega plus, sorry, omega minus plus del of omega plus 2 omega naught, right? Now, what is this equal to? sine of 2 omega naught t. This is pi over j del of omega minus 2 omega naught plus delta of omega plus 2 omega naught. Right. So we computed Fourier transform of the sine of 2 omega naught t. What are we left with? Fourier transform of this quantity. I mean, try it out. This is what you should get. So similarly, what you would do is take express cos in this, right? We express cos. How would you get these? The Fourier transform of these. These are respectively the time domain representation of frequency shift 3 omega naught t plus minus 3 omega naught t, right? When you would do that, you will end up with this answer 3 omega naught t. You would, in fact, we have this j as well, right? So j times this, check if you get the same answer. J by 2. So 2 pi. Okay. Essentially, what I can write this as j pi del of omega minus 3 omega naught plus we missed sign. Should be minus, right? Plus omega plus 3 omega naught. And then, okay, in the options, uh, what if we take this j pi common? If I take j pi common, j, j, I'll have j square in the denominator. That is a minus sign. So, right, this is the answer that I want. Sine of 2 omega naught t plus j cos of 3 omega naught t. Right, I'm taking j pi common. Be left with this. And then the, there would be a negative sign here and a positive sign here, right? Because this would be this. So there would be minus, there would be a negative sign for this one. So minus delta of omega minus 2 omega naught and a positive sign for delta omega plus 2 omega naught. And this is option C. Okay, so option C is correct. So let's go ahead to an easier question now. What is the Fourier transform of delta of 3t plus u of t? Today we saw what is the Fourier transform of u of t. Right. In fact, I would suggest you to memorize this result. You get following it's the Fourier transform u of t. Right. Pi del of omega plus 1 by j omega. So pi del of omega plus 1 by j omega. You are left with these two options. Right. And you need to see if you'll get this t or 1 by 3 as a DC term. Remember, we can write delta AT as 1 by modulus of A delta of t If I can do that, then I can write delta 3t as 1 by modulus of 3 is 3, right? And when I'll take the Fourier transform, we also saw that the Fourier transform of this delta of t is 1, right? Fourier transform of delta of t, that is 1. So if I multiply 1 by 3 on both sides, essentially I get Fourier transform of delta of 3t is, take this 1 by 3 factor out, Fourier transform of delta of t is 1. So which option is correct? Earlier we had shortlisted these two options. Which option should be correct? Option C, right? The
Yes,
correct
sir.
answer,
Option C.
yeah, option C is correct. With that, we'll move on to the next question. The Fourier transform of a continuous time rectangular pulse, which is unity for minus 2 less or equal to t less or equal to 2 and 0 otherwise, is which of these following? So remember this definition, how we had defined our rect of t by tau. One approach is to readily use this result, but we need to be careful with the notations. So this tau was the duration over which the signal was unity. Minus t by tau, t by tau. This delta tau would be tau, right? This interval would be tau for which the signal is unity. Okay, let me do one thing. I'll take this snap. Copy this and paste it the next page. Right, this was the result. So comparing this with our case, the signal is unity for this range, right? So let me draw the signal that is described in the question. Right, this is the signal. Suppose the signal is x of t, whatever. So now express this x of t in this form, right? I'm trying to first show the shortcut and then I'll tell you how alternatively you can do by another process. So what is tau? Compare this and this and tell me what should I write? As x of t as rect of t over what is tau?
2. 2.
Yeah, should it be 2?
It's been t divided by 2.
Yeah, t divided by 2. Notice the best way to remember this is in the notation that I showed you. It is unity for tau units, right? The period over which that signal is unity, that is tau. For what interval this signal is unity? For
Minus
how many?
2 to 2.
Yeah, and that evaluates to 4 units, right?
Yes.
So once you do that, then it is pretty straightforward. Then you will write, okay, so effectively, I need to compute the Fourier transform of this. I'll write Rect of T over 4. The Fourier transform of this is tau. What is tau? 4. Sinc of omega, tau by 2. What is tau by 2? 4 by 2 is 2. Agreed? Is this part clear?
Yes, sir.
Okay. So this is 4. Now this sinc function is the unnormalized sinc function. Okay, just make sure you remember that. This is not the normalized one, right? This is the unnormalized one. So by definition, I'll write sine of 2 omega divided by 2 omega, right? And then this is what you get. Agree with this?
Yes, sir.
So this is nothing but option D, right?
4.
Yeah, fourth option. So let me briefly give an outline of how you can do this problem alternatively. The alternate method to tackle such a problem is as follows. Okay, have you read about this property given x of t, the Fourier transform of x of omega? If I take the derivative of x of t, what should be the Fourier transform? Have you done this property? I mean, has this been taught?
Sir, I think I have not idea about this. So can you please
Okay,
explain?
okay. So proof you can see either in the week lectures, or if needed, you can mail me. I'll let you know how this comes about. Or in fact, you can readily try this yourself as well. This is j omega times x of omega. So given you have the Fourier transform, if you take the derivative in the time domain, the frequency domain representation gets multiplied by j omega, right? This is essentially the result. So in our case, this x of t was this function. Okay. If I say y of t is d by dt of this x of t, what should be y of t? I mean, what should be the plot? Help me out. What should be the plot? This is what I'm asking. Take the derivative of this plot on the right hand side. What would be this? Okay, notice it is 0 from minus infinity to minus 2, a constant 0, right? So readily you'll say that, well, this derivative will also be a 0, right? Regardless of this had been a 0 or a constant, right? And for this constant part would again be 0 till this point. But what about the points minus 2 and 2? the function jumps from 0 to 1. This is what we do. We say that this is delta of t, right? And this would be in fact a shifted delta t, shift by 2 units of time, right? That is minus 2. Delta t occurs here, right? Now I'm shifting this. This is delta of, in fact, we can write, do one thing. We'll say that this would be a delta function of magnitude 1 here. And what about at 2? What happens at 2? This function goes from 1 to 0, right? So what should I do? What would be the strength of this delta function? Is this part clear? What I did here?
Yes, sir.
Yeah. So the magnitude of delta function was this final value minus initial value, right? 1 minus 0. And the difference was 1. So this is what I wrote. Now it is 0 final. Initially it was 1. It goes from 1 to 0. What should be the magnitude of the delta function at 2? Could be minus 1, right? 0 minus 1 minus 1. So this is what it would be. Is it clear? I
Yes, sir.
hope so. Yeah. So then what we can write is mathematical form of y of t. What would that be? That would be, see, it's delta function at t equal to minus 2. So that is nothing but delta of t plus 2, right? And similarly, would be minus 1, right? In fact, plus minus 1. The magnitude of delta function is minus 1 at this point. Times, what should I write? Delta of t minus, I hope you are able to
2.
follow. Yeah, it is 2. So our y of t is delta of t plus 2 minus delta of t minus 2. So what I would do is I would evaluate the Fourier transform of this y of t. That is y of omega. This would be e to the power j2 omega, right? This would be e to the power minus j2 omega, right? And in terms of sign, what should I write? This translates to, in terms of sign, I can write this as 2j times sine of 2 omega. Is that okay?
Yeah, sir.
Right? Yeah. So that is what y of omega was. But currently, I'm writing a Fourier transform of the function y of t. And what is y of t? It is the derivative of our original function of whose Fourier transform we were interested in. Right? Then what I can do is I'll utilize this property. So now I know that j omega x of omega, this one, This one was the Fourier transform of the derivative of the original function, right? And we evaluated that as this one. We'll write this 2j sine of 2 omega, right? This gives x of omega as j and j would go, right? This would be 2 sine of 2 omega all divided by omega. And what is x of omega? X of omega is the Fourier transform of the original function x of t in which we were interested in. In this case, it would be the Fourier transform of this. So notice the answer that we got following this formula based approach was this 2 sine by omega. Sorry, 2 sine of, I wrote it in a wrong. Right? This is whole divided by omega. Similarly, I got the same answer. Okay, we saw two approaches for this question as well. Now this one is pretty straightforward. What should be the answer? The equivalent time domain function f of t means to what is the, I mean, inverse Fourier transform of this frequency domain representation, right? X of t, x of omega. If I say that this is x of omega, then what should be this? See, one way would be to use the result by definition, right? Use this inverse Fourier transform is this by definition, right? But since we have, I mean, it is expected that you should know this result that e to the power minus at u of t, the Fourier transform of this is 1 by a plus j omega. Okay, so what should be the correct answer? I hope this is clear.
Sir, I'm confusing option D or B.
Option D or option B? Okay, in one of the options there is j. Do you see j here?
Yes. No, no, sir.
J is not there, right? So this should be the
Yes.
correct one. In fact,
B.
this one should be correct, right? There is a minus sign. See, I'll write this result. The result is e to the power minus at u of t. Make sure you remember these elementary results of Fourier transforms of some functions. Okay, that will come in handy in solving problems and answering them quickly. This is 1 by a plus j omega. Okay,
Hmm.
so this one is the correct answer, right? Because a is 20. Okay, so the correct answer
Yeah.
is option A. Now this one is more interesting. What is the inverse Fourier transform of 1 by 30 plus j omega whole cube? A hint is, suppose I had given you what is the inverse Fourier transform of, stop, j omega. What would be your answer?
Mm, sir, option B.
Option, no, in fact, see, these options were made keeping in mind this function, right?
Hmm.
You cannot readily use that. I mean, this would be, imagine that this would be inside the integral, right? This would be a tedious integral to solve, right? So we have an alternative approach, and I'm basically developing a motivation for the same. Okay, so what I'm asking you is, what should be the inverse Fourier transform of this basic function 1 by 30 plus j omega? Notice this is similar to this, is it?
Yes, sir.
Yeah, and if this is the result,
E raised
what
to
should
minus 30 j omega.
e to the power minus 30t, right?
30 t.
J
हाँ.
won't be there in the time domain. E to the power minus
Yes.
30t u of
T.
t.
U of t.
This would be the answer, right?
Hmm.
But we have been asked to find this function, right? Now, tell me one thing. This is of the form 1 over x, right? So if I give you 1 over x and I tell you that you take this derivative of this 1 over x, what would be the derivative of 1x, 1 by x? 1 over x
S raised to
is
0.
x raised power minus 1, and
Hmm.
d by dx of x raised power minus 1.
S raised to minus 1.
This would be minus 1 x raised power minus 1 minus 1. Is it?
Hmm.
This would be minus 1 over x square. Would it be this x raised power minus 2? I've taken that in denominator.
X raised to square, right, sir?
Fine. So derivative of 1 over x gives us minus 1 by x square. Fine. What if we take the derivative of 1 over x square? Do the similar process and tell me what should we get.
Minus 1 divided by t square.
In
T
fact,
raised to 4.
minus 2, right? Minus 2.
Hmm.
This is, suppose this is d by dx of x raised power n. What is that? That is n x raised power n minus 1. Okay. So this 1 over x square is x raised power minus 2, right? So this is minus 2 x raised power minus 2 minus 1. That is minus 2 x raised power minus 3. That is
3.
minus 2 by x cube, right?
Yes, sir.
So taking derivative 2 times gives me, yields me this function, right? From this function. So
Hmm.
now what I would do is I would use the property. See, this is, see, I'm now talking about taking derivatives in frequency domain representation. Before that, I was doing this, right? Taking a derivative in time domain representation. So let's first see what is the formula. If we take the derivative of the frequency representation, see, x of t, x of omega. What if I do this d by d omega x of omega, right? This is minus jt times x of t.
Hmm.
Okay.
Okay.
And then if I take the derivative again, how would you do that? Now see, earlier I used this property on this result. What if I use the same result on this one now? This would be d2 by d omega square, right? Derivative of the order 2 x of omega. Now, what happened when I took a derivative? This minus gt got multiplied, right? So when I'll take another derivative, this minus gt would get multiplied again. Okay. In other words, this would be minus gt square x of t. Okay, I hope you don't lose track of things. So this is what I would use. Okay. Now I'll first write the result for which the answer is pretty straightforward. In fact, you answered that already. You agreed that e to the power minus 30t u of t would be, I mean, the Fourier transform of this would be 1 by 30 plus j omega, right?
Yes.
You already answered it.
Mm.
Now what we would do is we will take would differentiation. We'll take differentiation of this 2 times to get this, and we'll substitute this value and get the time domain representation of that. I hope the idea is clear. We'll take the derivative of this expression 2 times and equate that to this. And the inverse Fourier transform of that resulting function would be this one. Okay, let's do this and it will be clear. So what is the differentiation of this 1 by 30 plus j omega? What is d by d omega of this? Using u by v rule, it would be this 30 plus j omega square, right? And then denominator times differentiation of numerator. Differentiation of numerator is 0. And then minus, so I'll use a minus sign. Numerator times differentiation of denominator. Differentiation of denominator is j. I'll use minus j. Okay. Let's not lose track of things. This is right. Minus jt. Help me out. Minus jt. What was x of t? Compare these two. Tell me. What was x of t? X of t was this, right?
Mm.
And I'll substitute x of t here, similar to this one. So using that, I'll have this e to the power minus 30 t u of t. Now I'll do this process again. When I'll do that again, I would get the following. Now this minus j. Okay, one more thing. You have this minus j on both sides, right?
Yes.
So you might as well cancel them.
Mm.
You'll be left with 1, right? Just to simplify the things. Now, what is the differentiation of this one? Again, you would use u by v rule. 30 plus j. I guess I should write d by d omega of this. You know, right? Suppose this is some y of t. What is this? D by d omega of this one. We write the answer. Turns out this is I guess we'll figure it out. 30 plus j plus down to omega raised to the power 4 one times, in fact 2 times the differentiation of this, that is j. Okay. This is nothing but I'm taking the derivative of denominator, numerator times denominator, because the differentiation of numerator would anyways be 0. What would this be now? This would be minus jt times which function should I use here? Should I use this function or should I use this function?
Mm, second, sir. E raised
Yes,
to minus 30t.
would be t e to the power minus 30t u of t. Okay, so now again I would cancel. Wait. I missed out one thing. I did not took I did not take this derivative properly. This would be 2 times 30 plus j omega, and there would be a j, right? Differentiation of denominator would be this. Then I can write, I would divide, I mean, this would cancel with this 4 and leaving 3 in the denominator. So I can write minus 2j whole divided by 30 plus j omega cube. Okay. So in this function, now I can cancel minus j on both sides and take 2 on the left side. I'm doing 2 things simultaneously. Okay. Or in other words, I'm dividing both sides by minus 2j. If I divide both sides by minus 2j, I would get agreed.
Yes, sir.
This would be 1 over 30 plus j omega. And we were asked to find what is the inverse Fourier transform of this particular function. And that is what we did, right? So what is the inverse Fourier transform of this function?
1 upon 30 plus j omega cube.
Yeah. And then which option should be the correct one? Looks like C, right?
C.
Yeah, it should be C. So that is question number 8. And then we have one last question. It's pretty straightforward. And in fact, this particular question was already done in today's session. This is part of that. The inverse Fourier transform of 1 over 3. What should be the inverse Fourier transform of 1 over 3? See, I'll write the basic result for you guys. Given delta of t, the Fourier transform of delta of t is 1, right? So if we have 1 over 3, what should be this?
Delta t divided by 3.
I guess you mean this one. We'll divide both sides by 3, right? Dividing both
Yes.
sides by 3 would give us this one. But I had shown you guys a formula in the second last session that what is delta AT? This is 1 by modulus of A delta of T, right? So what is delta of 3T?
upon 3 delta T.
Yeah, so what should be the correct answer?
Mm, option
Which option?
option first.
Yeah, and that is the correct answer. Okay, make sure you understand why it is not this one, right?
Yes,
We
yes,
use
yes.
this one. So
Sir,
yeah, please go ahead.
yes, sir. I have asked one question for you. Can you please solve
Okay,
this?
okay. Sine of omega naught t minus j cos of omega naught t. Oh, okay. We put these value e. I guess you are talking with reference to this one.
Mm,
Yeah, I guess this question would have been with reference to this one, right?
yes, sir.
Yes, you would do exactly same. And these are in fact identical questions, right? Just that you don't have factor here. You have, I guess, a negative sign here. And then this 3 is 1. This 2 is 1. Same question, right? Repeat of this. If you understood this part, then I'm sure you would be able to obtain the value of this, right?
Yes, sir.
Yeah, try this out. Any other question
No, sir.
regarding today's session or in general?
No, sir.
Okay. Yeah, that's all then for this session. We'll end this session here. Thank you.
Okay. Thank you, sir.